Okay, hi everyone. So this is a video to cover how do we tackle the post NWA1 extra practice questions that we had during our lecture. Okay, so without a further ado, let's dive right in to tackle problems involving the integral and also our what do you call integral and also this Riemann sum. Okay, so let's go to question 1. Okay, so question 1, we are tasked to find this thing over here, 1 over 1 minus cos. So for this one, we generally we would like to make the integral to be a very simple trigo function. Okay, so what do I mean by this is we observe that there is a 1 over here, right? So we will want to try our best to get rid of this 1 so that we can get a single trigonometric stuff. Okay, so how do we do so would be like this. Okay, so in our MF27, you can actually see that there's a list of our things over here, right? And I think notably, which one allows us to change away cosine x? And at the same time, right, there is a 1 over here that we can actually use to get rid, there is a 1 in the formula that we can use to get rid of this 1 over here, right? So roughly speaking, as much as possible, I would want to minus a positive 1 if possible, right? So the idea would be to look at the 1 minus 2 sine square LA, this one, okay? The double angle formula, and specifically this one over here, okay? This last one over here, okay? So without further ado, okay, so we will rewrite this as, okay, 1 minus, so applying the double angle formula, right? So cosine 2a would be equals to 1 minus 2 sine square a, right? So with this over here, let me rewrite this into 1 minus 2 sine square. Then half of this angle would be x over 2. Okay, so the idea is to make use of the double angle formula in order to get rid of the 1 over there. Okay. Okay, so with this, right, we can roughly see that the next step will be really, really convenient, right? It will become like this, right? Which is very simplified. And then bring the half out. Sine 1 over sine, right? I can change this to cosecant square x over 2 dx like that. Okay. Okay, so with this over here, right, what do we do next over here is that how do we integrate cosecant square? So this one you have to recall from your differentiation, because this one is not in the MF27. So recalling from differentiation, right, you know how to differentiate sine, cosine, tangent, right? And at the same time, right, you can extend in A level to differentiate cotangent. So differentiating tangent will give you secant square, so differentiating cotangent will give you negative cosecant square, like this. Okay, so with that, right, the integration over here, right, would be half. So integrate cosecant to get your negative cotangent x over 2. And because of chain rule, at the same time, we need to divide by half in front. Okay, then plus c. And so because of that, altogether, this would give us negative cotangent x over 2 plus c. Okay, so this one just need to take note. Okay, so once again, this cosecant square, right, is actually extension from O level, right? We already considered tangent. So to differentiate cotangent, it will get us negative cosecant square. So the integral is just to go reverse. So make sure that you remember what you learned in the differentiation chapter as well. Okay, so that will be for method 1. Okay, method 2 will be a little bit tedious, but it requires us to use something like we call the so-called conjugate of the denominator. Okay, so it will look something like this for method 2. Okay, so for method 2, right, it is to consider the so-called conjugate of this thing. So it will look something like this. So 1 plus cosine of x at both the numerator and denominator. We need to multiply by 1. Okay, so with this, right, we can actually see that at the bottom, a square minus b square will give us 1 minus cosine square x, right? And on top, it will get 1 plus cos x, like we multiplied earlier. Okay, so with this over here, we will simplify the 1 minus cos square by our very famous identity over here, right? Which is actually sine square x dx. Okay, now then with this we can split the fraction, because now with the idea is to get the denominator into one term so that we can split things up differently, and then we can integrate one by one, right? So once we get this out already, 1 over sine square is actually cosecant square x, right? Then cosine x over sine x, we can rewrite this as something like this. So cosine x over sine and 1 over sine. We can write something like this, right? So this tells us that we will get something like a cotangent x and a cosecant x dx. Okay, so I can simplify it to something like this. Okay, so then what do I do next is to consider what integrates, what differentiates to cosecant square. So like what we see just now is actually negative of cotangent x. Okay, that differentiates to cosecant square x. And what differentiates to cot and cosec? This is actually minus cosecant x, then at the end plus c. Okay, so this is the thinking that we need, right, in order to get our integral out. Okay, so the idea once again, right, is that we want to simplify the denominator so that we'll get only one term to integrate. Okay, regardless of using this identity, right, using the conjugate to obtain the identity, right, or to use the double angle formula and get rid of this one to reveal just a singular term. Okay, so then you see that both of these answers, right, may look very different, but actually they're the same function. Okay, notice that this is x over 2. The argument or the angle here is x, a bit different. Okay, so here we go with our question 1. Then for question 1b, moving on to question 1b, we are required to make use of the substitution to find this thing over here. So whenever we look at the substitution, right, integration by substitution, let us remember the keyword LED. We need to do all three LED. We need to sub in the limits, with expression and the differential all together. Okay, so maybe for me, right, at one side I will write out what I need to replace for the limits and even the differential. Okay, so let's start with x equals to secant theta. So this is where I'm starting off with, right? So 2 secant theta, right? So the thing is, I want to do dx d theta. So let me differentiate this one time so that I can put in the differential. Okay, so differentiate secant, I will get secant and tangent. Okay, so this one is the official thing to do. Then the unofficial thing to do next, okay, the unofficial thing to do next would be to rewrite into something like this: 2 secant theta tangent theta d theta. So dx would be replaced with all of these things over here, okay, illegally. Okay, so let's do this. Let's do all the substitution now. So starting with the thing that they gave us. Okay, so let's do the substitution now. So x cubed, right? So replacing x with this, so I would have 8 secant cube theta. Okay, and a 4 secant square theta on the inside. Okay, so this would be the substitution that I will make. Okay, so that's for the expression. Then the differential, right, I need to replace this with 2 secant theta tangent theta d theta. Okay, so when you replace also, let's replace everything one shot. Okay, so there we have it. So now the next trouble is to try to simplify this. Okay, so the first thing that we want to simplify would be to simplify this radical over here, the square root over here. So taking out the 4, I think you can see that this is secant square minus 1. So secant square minus 1 would be an identity over there. Okay, okay, so the identity being that this is secant square minus 1 to be equals to tangent square theta. So I'll need to leave the tangent, I'll just need to replace the whole thing with a tangent square after that. Okay, so at the bottom being the same, okay, secant cube theta. So 4, right, bringing out the third will give me 2. Okay, square root of 4 is 2. And within the square root, I will have a tangent square over here. Okay, so all these things over here, 1 over 2 secant and tangent d theta like this. Okay, slowly one by one. Okay, so let's do a little bit more cancellation now. 2 and 4, 2 and 8, I can simplify to 4, right? The secant and this secant um, square can, secant cube can be simplified. Tangent square, square root, and tangent can be simplified as well, right? We can do a lot of cancellation at this step. Okay, so after you do some ninja moves and cancel here and there, I've got 1 over 14, 1 over 4, sorry, still 1 over 8 on the outside. Okay, and then on the inside over here, I will have 1 over secant square theta. Then the rest are all cancelled away, so like that. Okay, so this is it, secant square theta. Okay, then after that, 1 over 8, right? Secant square is just 1 over cos. So change this to cos square theta d theta. Okay. Then the next thing is cos square, right? Is actually how do we integrate squares again? We integrate squares using our double angle formula, namely this one, cos 2 theta equals to 2 cos square minus 1. Right? So making cos square the subject, we can see what to replace. So this one over here will be our standard A level thing lah. So you must know how to integrate squares. Okay, so this one would be cosine of 2 theta minus 1, look like bin, over 2, then d theta. Okay, so with this, I pull out the 2, I get 1 over 16. So integrate cos 2, I will get half sine 2 theta, then minus theta, and plus c. Okay, so far, right, we've carried out the integration by substitution, right? So what we did again is to substitute in these things over here and also to substitute in the differential. Okay, so a lot of students forgot to put in the differential, and we do some simplifying by using our knowledge from trigonometry. So simplify all the way until a very simplistic thing like this. Okay, so this is the first wave of things to do. Now, because this question is indefinite integral, so means that we do not have a final value to calculate. So if you have a final value, very nice. We have to change the limit and just sub in the limit into this expression to get our final value. Okay. However, we don't have a final value yet, means that we must change back our answer from theta to be expressed in terms of x, because originally it is x. So how do we do so with this? Okay, so with this, right, the problem is that for the standard technique to do for substitution, trigo substitution actually, right, is to recall the earlier substitution that we made. Okay, so x equals to 2 secant theta. So x over 2 would become secant theta, right? Then 2 over x will be equals to cosine theta. So this is the first thing that we need to take note. Okay, right? And then more or less, right, we will need to construct a right angle triangle using this information over here. Okay, so the right angle triangle would be as such. Okay, so we have our theta over here. Cosine means that is adjacent over the hypo. Okay, then by using some Pythagoras theorem, we actually get the opposite side over here, which is going to be x squared minus 4. Then we square root this thing over here. So this will be the hypo side. Okay, now then you notice, right, because we started off with theta, right, over here the expression is 2 theta. So what do we need to do? We have to break this and prepare this by using the, what do you call this, the double angle formula. So the double angle formula for sine 2 is 2 sine theta cosine theta, okay, minus theta plus c. Okay, so now this being ready, right? So let's put this in. So 1 over 16, half and 2 will cancel out. Now, sine theta. According to this triangle over here, what is sine theta? Opposite over hypo. So the expression would be like this. X squared minus 4 square root all over the hypo x. Cosine theta. Cosine theta is what we've got just now, 2 over x. Okay, and then for last but not least, the theta over here. Now this theta, right, we can actually get from here. Okay, this theta we can actually get from here. Cos inverse of 2 over x is equals to theta. So I will just make use of this for the substitution. Okay, so cosine inverse 2 over x. Okay, plus c. So let's tidy this up now. We've got 1 over 16. Okay, or maybe, okay, if you want to open the bracket, right, 1 over 8, or maybe, okay, this one minus 4 divided by 8x squared, then minus 1 over 16 cos inverse 2 over x plus c. Okay, so this would be our final answer. Okay, so once again, right, I'm here to tell you that this question over here is a very standard substitution technique question. Okay, so the thing is that the standard technique is to remember to do the e and the d expression and differential. If it is a definite integral with limits, we have to change the limits as well, and we change this all at one step. After that, we make use of our trigo things to simplify and integrate all the way to theta first. After integrating to theta, then the standard technique to change it back to x is to consider the original expression and to rewrite the expression into sine, cos, and tangent that we know earlier. So using sine, cos, tangent, build the right angle triangle to get the expression for x so that we can do the replacement back into the bracket over here. Okay, so this is the idea behind our integration by substitution. Okay, so hopefully this will seem hard at first, but the steps are very standard. So what you need to do is just to find 2 or 3 more examples and redo. Okay, do again so that you can see roughly the pattern and the technique that we're going to do for this one. Okay, so moving on to question 2. So this structure looks very familiar as compared to your O-level days. Part 1, differentiate. Part 2, integrate, right? So I think from your O-level days, you can see that actually this is a integration as a reverse of differentiation, right? So likely we'll need to make use of the results from here to apply it to here. Okay, so let's do our part 1 first. Okay, so this one we have to chain very carefully. Okay, so from here, right, you can see that we are going to differentiate 3 stuff. Okay, so first, differentiating the e will give us back the e. Okay, next, differentiating the cosine will give us a sine. Then differentiating the x over 2 will give us half. Okay, so hopefully you can see that we are differentiating 1, 2, and 3 things over here. Okay, so putting all of these together, this will give us sine x over 2 e to the power of cosine x over 2, like this. Okay, the 2 and a half cancel each other like that. Okay, so part 1, easy, no worries. Okay, part 2, hence find that thing over there. So, okay, let me write out this thing over here first. Now, because we want to use integration as a reverse of differentiation, right? So how do we reverse this back to here? We have to match this to the form in part 1, right? So this e cosine x over 2, right, has already been matched. They are identical, so it's fine. But however, we have a sine x as compared to sine x over 2. This over here is what we need, right? So how do we express this thing to what we need? So that's the question. So observe that this is x. This one over here is x over 2, right? So what formula or identities that you know that can change x to x over 2? So this is your double angle formula, right? So because of this, making use of the double angle formula for sine, we can change this to 2 sine half of the angle cosine half of the angle, like this. Okay, then let's rewrite and rearrange this, right, such that I lump these two things together, because I can integrate this all the way back here. Okay, so I will rearrange this to look like something like this. Right? So now over here, right, notice that we have more or less a product over here, right? So to integrate products, right, first we want to check whether is it FF prime. The idea is this is not FF prime, right? There are two different things, so it's not related. So the other technique that we can use over here would be to, okay, so this is F prime F, right, which is not. And then the other one to do is actually integration by parts. Okay, so this one to differentiate, this one to integrate, because we can integrate this back to the question, right? So more or less this is given to us already, right? So to differentiate, right, I will let this be u. To integrate, I will let this be dv dx. Okay, so writing out our u, so u equals to cosine x over 2. So differentiating this would be negative half sine x over 2. Okay, then dv dx over here, okay, would be, okay, let me adjust more space. Okay, so integrating this will give us our 2 e cosine of x over 2. Okay, something like this, right? And the formula to integrate by parts, right, u dv, would be to do ultraviolet voodoo. Okay, so this is the formula to integrate by parts. Okay. Okay, so let's carry out this integration now. So this one over here would be uv. So would be cosine x over 2 multiplied by 2e cosine x over 2. Okay, minus the v du. So minus integral of v du. Okay, negative 1 over 2 sine x over 2 dx. Okay, so let's rewrite this. Okay, so this will look something like this. Okay, then the one in the integral would look something like this, right? So you can see that actually this one, right, you're making use of the result another time to go all the way back to here. Okay, so last but not least, we will have something like this. Now, is this extremely difficult? I would say that it's not quite difficult, right? I think what you need to have over here is just some sense of observation, right? To see what's going on and to find out how do you link this current part 2 to the previous part, so that you can just integrate nicely. Okay, so this is not too difficult, but it requires you to break down and to see and link back to the previous one. So that's why it may seem challenging, but actually it's not so challenging. Okay, so hopefully you can see the integration by part, and then I think hopefully you can see that you have to use the part 1 to apply this in part 2 by reversing your result. Okay, so this is the essence of question 2, right? Using integration as a reverse process of your differentiation. Okay, so question 3 over here would be a question on Riemann sum. Okay, so the idea for Riemann sum, right, is that this would be the origin story of our area under graph, or area between the graph and the axis. So Riemann sum, right, actually means what is mainly just the area between your curve and axis are just sums of rectangle. In essence, right, how do you get your area of a rectangle? Would be your base times your height, right? Base times length or base times height, whichever you see in this question. Okay, so over here, so let's do our setup over here, and with the aid of a sketch, right? So likely we'll need to sketch a graph, right? So given that f is a strictly increasing continuous function, okay, strictly increasing continuous function, so means that the function, right, must increase. It cannot be stationary. Okay, stationary means it cannot be constant. It cannot have a turning point like that, right? So because this is decreasing in the middle part, has to be strictly increasing. Okay, cannot be like this also. Okay, because this part is decreasing, right? So strictly increasing continuous function. So let us do the sketch first. Okay, so this would look like a strictly increasing function. Okay, so it just increases. Okay, so why this is less than this over here? Okay, so let's not worry about this idea first, right? So worry about the less than first. What we want to do is we want to try to equate the sum of the area of rectangle, right, to the area between curve and the axis. So this over here, right, is the area between the curve and the axis. This one over here, right, is the sums of the rectangle, right? Can you see that this is your base? And all these things over here are your heights. Can you observe this? Right? So because of this, right, we can try to indicate the the rectangles under this graph. Okay, so over here we are going to build rectangles, and the first height that we're going to use, right, is at 0. Okay, so when x equals to 0 over n, which is 0, so fx is actually this height over here, like this. Okay, so here would be my first rectangle. Okay, then my second rectangle, so this is 0 over n. This is 0 over n, right? Then my second rectangle would be over here. Okay, this is 1 over n. Then putting 2 over n over here, my rectangle will look something like this. Okay. Then putting 3 over n over here, right? When x equals to 3 over n. So this is the rectangle that I will get. Okay. Likewise, I can do again and again to get you your rectangles out here. Okay. Can so up to the very end, okay, you can continue this process, right? Dot 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 dot. Okay, up to the very end. Okay, when you have n minus 2, okay, this is going to be your rectangle. Okay, then the next one after n minus 2 will be n minus 1. Your rectangle will be like this. Okay, all the way up, this and like this. Okay, last but not least, it will be n over n. Okay, where your rectangle will be like this. Okay, now then you double check again, right? Double check again and see whether how many rectangles do you need to take up. So you start with 0 over n. So when x equals to 1 over n, this is your rectangle, all the way actually until n minus 1. So actually, right, you don't need the last red color rectangle, you just stop over there. Okay, until n over n. Okay, something like this. Okay, can so this is the sketch that I will get you to do, right? And one thing that I would like you to also see, right, is that this height over here. Okay, this height over here is f of 0 over n. This height over here is f of 1 over n. this height over here is f of 2 over n, and so on and so forth. Okay, so hopefully you can see this. And last but not least, this height over here, okay, okay, let me shift this a little bit. Okay, this last height over here is f of n minus 1 over n, something like this. Okay, so these are the various heights from the graphs. Okay, okay, so the first point over here would be used to describe the process of constructing n rectangles, each of width 1 over n, as the diagram beside, and the total of the rectangles can be used to estimate the area under the curve from 0 to 1. So what we are doing over here, right, is that we are using the area of the rectangles to estimate the area under the curve. Okay, so this is the essence of the Riemann sum. So point number one is to talk about the essence of Riemann sum. What does it do? What does it take to do a Riemann sum, or what does it really mean by area under the graph, right? So with that, right, what do you do next is to observe the area of the rectangles and the area under the graph. So you can see that the area under the graph, right, has more parts because of these empty blanks over here that the rectangles cannot cover. So these are what we call underestimate. So the area of a rectangle, right? So the sums of the area of rectangle is an underestimate of the actual area under the curve. Okay, so from the diagram, the second point that you can make is since, right? Okay, so writing something like this. So maybe let's pretend to find the rectangles. So the base times height plus base times height plus base times height. Okay, all the way until base times height. Okay, it's essentially just base height, base height, base height. And this one over here, right, factoring out the 1 over n would give us the expression that we see above. Okay, factoring out the 1 over n will give us the expression that we can see all the way above over here. Oops, this one. Okay, let us see this one over here, right? So this one, right, would be less than area of curve. And how do we write the area of curve? From 0 to 1 of fx dx. Okay, so just like that. Then we shown. Okay, so this show question, right, is mainly a description question lah. Okay, usually show questions for Riemann sum would be a description question where we need to describe the process of building the rectangles over here. Then we want to show whether is it more than or less than, or roughly equals to as the limit of the n goes to 0. Okay, as the width of the thing become very thin. Okay, so this is the essence for the Riemann sum, and how do we write this? So moving on, right? Hence, so hopefully you can really see that what we're doing here, right, is actually, right, it looks difficult, but essentially the idea is just base times height, base times height, base times height, all the area of rectangle together less than area under the curve. That's all. And how do we construct the area rectangle with that tick notation over there? So that's the idea for this kind of thing, right? So hence, find the least exact value of k such that this thing would be less than k. So roughly speaking, right, this one over here, we need to do some integration. We try to match this to the fx. Okay, so f of 0 over n is e 0 over n. F of 1 over n is e 2 over n. Oh, this is interesting. F of 2 over n would be 4 over n, right? So if you were to notice this for part 2, okay, for part 2, the fx is actually e 2x. Make sense? You sub in 1 over n. This is 2 over n, right? Sub in 1 over n, you get 2 over n. Sub in your 2 over n, you get 4 over n, right? Make sense? So fx is equals to e to the power of 2x, right? So this means that 1 over n of this one all the way until e of 2n minus 2 over n, right? This would be less than integrating 0 to 1 of e2x dx. Okay, so this one over here is the fx. Okay, fx dx from 0 to 1. Okay, right? So now what we do, right, is we try to evaluate this over here. Okay, so this one to integrate, right, this is actually half e2x from 0 to 1. So this one, when we do some math, this is actually half of e square minus 1. Doesn't look like a constant, but it actually is a constant. So the least value of k, okay, would be half of e square minus 1. Okay, so that would be the answer for part 2. Okay, applying the Riemann sum on this thing over here. Okay, so hopefully you can see that this one, initially it is very off-putting, right? But I think once you do once in your tutorial already, another time you see this in see this now. So hopefully you can see that the essence is pretty much the same. And I think you try one more question, one more similar question, right? You can really see how to answer this with confidence already. Okay, so hopefully this even though it looks very tough, but it makes sense to you, right? Then hopefully through making sense, you're able to write in your own way, but still following the notation given in the question. Okay, so that's the idea for this one here. Okay, so let's look at question 4. This one over here would be a volume and area problem, right? So let's take a look at, so it is important for us, right, for whenever we see questions like this, right, to get a visual of what's going on, right? So what I want to recommend is first, okay, to put this in your GC first, okay? So key in this, okay, so if you notice, right, this equation over here, right, there is going to be a plus and minus, right, when you make y the subject. So because of that, I will need to pull out these two graphs so that I can see the full thing. And I also put in the y equals to x over here. Okay, so taking out this one and putting here, right, so the image of the graph that I will get would be this. Okay, so now let's look at this and let's see what are the important points and what are the crucial points to look at. Okay, so by taking this, because this is already a completed square form, right? So what we can see is that by making x the subject over here, the point, the so-called turning point over here is here. Okay, where x is 4, y would be -2. Okay, by rearranging this and looking it in the lens of a completed square form, right? This is the one that we'll get. Okay, and I think using GC, right, you can actually get this point as well. Okay, so this point over here is -5, -5. Okay, so now that we've gotten these 2 points out, right, so roughly we can see how do we get our the area that we want. Okay, so find the volume generated when S is enclosed by this curve, right? So where is S? S is over here. Okay, so when S, which is highlighted in gray over here, is rotated 2 pi radian about the x-axis. Okay, so what does this mean over here? Now, so with this, right, hopefully we can see that now we have this area over here. Sorry, this volume generator over here, right? And what you need over here is to minus away this cone, correct? So this cone on the inside will be taken out. At the same time, right, the area inside here will also be taken out. Sorry, the volume inside here will also be taken out, right? So this one over here is a hollow part. This one over here is another hollow part with the cone, right? So hopefully you can see that the area, the volume, right, is actually in this few things here. Okay, so it will be this one minus away the cone minus away this part over here, right? So this will be our volume generated when x is rotated about 2 pi radian. Okay, can so over here, right, we will split this, right, to we can do this in two different ways. Okay, we can write this in two different ways. So method 1, okay, is to write this as the big area minus the two smaller area, big volume minus the two smaller volume. Okay, so for this red piece over here, right, this big volume over here, right, so where is it from? From -5 until 4. Okay, so integrating from -5 until 4. Which function is it defined? It is defined by this function over here, the red color function. And this red color function is this one over here. So defined by -2 minus this one over here, 4 minus x. Okay, and then because this is volume, right, so pi x square so pi y square dx, so pi y square dx, like this. Okay, volume of the thing. Okay, so now we settled the red color volume already. Okay, so now we have settled this. Okay, so let's take a look at the second one. This second volume over here, we need to minus away the cone, right? So there are two ways in writing the cone. You can write this using the 1 over 3 r square h, pi r square h, right? Otherwise, you can also do the integral for this one. So this one integrating, right, from where to where? From -5 until 0 of this curve over here, right? So here I can write this as minus pi from -5 to 0 of the function square dx, like this. Okay, you can do this. Okay, last but not least, the blue color area. This one I need, sorry, blue color volume, right? Now from where to where? From 0 to 4 of this blue color curve. This blue color curve is actually y1 over here, right? So writing this over here will give me, okay, from, okay, pi from 0 to 4. Okay, maybe I write another line. Okay, of this one plus, okay, like this. Okay, then typing it all into the calculator, we should be getting 327.25 units square, the cube, for volume. Okay, so this is method 1. Okay, method 1, taking the big volume minus all your small volumes. Okay, so this is method 1. Okay, so for method 2, we can think of it as an outer volume minus the inner volume. So what does it mean over here? Now, if you were to refer to this one over here, right? Right? So we have to split all of this into two different sections because we are concerned with two different mainly two different sections over here. Okay? Okay, so the required volume over here, right? So we need to split to two sections. The first section, right, is from here to here. So this is x equals to -5. This is x equals to 0. Correct? So what we're going to do, right, is for this one over here, from -5 to 0, pi. Okay, the volume on the outside is given by the red color one. The volume on the inside is given by the black color curve. So we can write this as pi of the red color volume, which is generated by this. Okay, then minus of the black color one, which is generated by x, and then holding the x. So this is the first section, the section on the left. Okay, then the other section over here, right, would be the red color volume, so minus pi. So this is the first bracket, or the first thing. Okay, the second one, minus pi from 0 to 4. Okay, from here, x equals to 0, x equals to 4, of the red color volume, which is this one over here, right? Minus away the blue color volume, which is here. Okay, the volume on the outside minus the volume on the inside, dx. Okay, so altogether, when you put this in, right, it is also the same 327.25 units cube. Okay, so hopefully you can see that both methods will work, right? And then you just choose the one that you prefer to do. Okay, ultimately both will work, so just choose one that you know that will work, and then you just keep doing it consistently. Okay, so that would be for the method 1 and method 2. Okay, now then find the exact area of S. For S over here, right, actually it would be more convenient, right? If you observe, right, it will be more convenient to actually do by dy. So if you look at this, right, this the it will be the right curve minus the left curve to get this area over here. Okay, so the easier method would be this for part 2. Okay, so the area, right, would be the right curve minus the left curve dy. Okay, or it would be the curve above minus the curve below dx, like that. Okay, so with this, let's go with the right and the left lah, so that we can roughly see what to do. Okay, so roughly like this. This one can throw, then this one can put here. Okay, so the curve on the right, okay, so the required area over here, okay, would be the curve on the right. So the curve on the right, right, making x the subject from here, making x the subject will be 4 minus that one square, right? So it will be 4 minus x plus 2 square dy. Okay, sorry, this is y plus 2 square. Okay, can so this one, right, on the right minus the one on the left. So this one would be y dy. Okay, and then from where to where? From, sorry, the limits, right, is actually from -5 until 0. Okay, follow the limits on the y. Okay, -5 until 0. Okay, so with this, here we can see and slowly integrate this one to be 4y minus y plus 2 cube over 3 minus y square. Okay, we can sub all this in, so this will be 0 minus of, okay, -20 minus, okay, found something over here. So this one actually y square over 2. Okay, so this one, okay, I think it will be a plus 9 over here. Then this one over here would be minus 25 over 2, I suppose. Okay, one more missing one. Okay, this one would be just 0. Okay, so this would be 0, and then this would be minus 8 over 3 actually. So this one give me altogether 125 over 6 units square. Okay, then obviously we can also do, right, obviously you can also do the curve above minus the curve above minus below between two sections. Sure can, right? But this one will be a bit more tedious because we are looking for the exact value. So imagine we need to integrate two different sections like this. Okay, can so this is how we will work question 2, by observing that actually, hey, this one over here we only need to look at dy, right? Then you integrate with respect to y. Okay, so that's all for this video. Hope it was enriching, and see you again in further videos on the more revision for AOI and also Riemann sums. Okay, so that's all. Bye bye.